Hi, everyone. Good evening. We just have a few folks. Oh, looks like everyone's logged in. Perfect. Thanks for joining us, everyone. Thanks for taking some time out of your evening to be with us tonight. My name is Jenna. I'm a initiatives coordinator with the Community Energy Association, and I'll be here guiding you through our first webinar of the Improve Your Home Energy Efficiency Retrofit Journey. So we'll just get started right away. I know everyone's taking some time out of their evening and we have an hour and a half here. So just next slide there, please, Murray. Perfect. All right. So again, my name is Jenna. I'm calling in from what is now known as Nelson, but for thousands of years has been the traditional homeland of the Snakes Nation, the Silks Nation, and the Ktunaxa Nation, and is home to the Métis and many diverse Indigenous peoples. As part of CEA's commitment to truth and reconciliation, we recognize the importance of amplifying Indigenous climate leadership. So I wanted to start off today's session by sharing a bit about Akiskunuk's retrofit journey. So Akiskunuk is a Ktunaxa community that's near Invermere in BC, and their retrofit journey began in 2008 with the introduction of a Ktunaxa Nation energy manager that focused on laying the groundwork for future energy planning and sustainability initiatives and established a comprehensive understanding of community needs and opportunities in energy efficiency. In 2010, an energy and emissions plan was created for Ktunaxa Nation, creating a framework for reducing energy consumption and emissions within the nation. From 2013 to 2016, the community was introduced to the Engagement with Energy Conservation Assistance Program, or the ECAP program, to support with retrofitting homes to make them more energy efficient, comfortable, and healthy. In 2017, a series of community workshops and hands-on demonstrations supported increased energy literacy for community members and created opportunities for feedback from community on their priorities and needs for housing. So this involved a week-long training for community members in partnership with Think Bright Homes in Invermere and funding from BC Hydro. In 2018, community homes received free energy assessments and quick fixes to improve the house's energy efficiency. And these included draft proofing, air sealing, high efficiency light bulbs and shower heads, air filters, and pipe insulation. Learnings from these assessments and quick fixes identify the next steps, a bundled approach to repairs and retrofits. So in 2019, Akiskunuk took this bundled approach where they worked to improve the air tightness, insulation, windows and doors, and mechanical systems in their homes. In 2020, a significant milestone reached with the successful retrofitting of 10 elders' homes. So this focused on improving the living conditions of elders by making homes more energy efficient and ensuring the homes are more comfortable, healthy, and sustainable for future generations. So if you move forward to the next slide there, please, Murray, I'll just share some learnings from Think Bright Homes through this experience that I think this audience would find relevant to maybe their journey through their own retrofit. So the biggest learning was the importance of taking the envelope first approach. So looking at air tightness and testing, exterior insulation, windows and doors as first priority before considering mechanical systems. There's also the importance of having an energy audit completed before and after to better understand what upgrades your home can most benefit from and what impacts those upgrades had on your energy use. So CEA, we've had the honor of walking alongside Akiskunuk through some of the stages of their retrofit journey, and we learned a lot from their story, and from those learnings and others, we continue to walk with other First Nation and settler communities to support similar processes and positive outcomes. So it's my pleasure to share this success story with you and to continue to amplify and feature the successes of Indigenous communities across BC. Next slide there, please. Perfect. All right. So who are we? The Community Energy Association, or CEA, for those of you who are not familiar, we're a registered charity, a nonprofit that's committed to accelerating bold action by local governments and Indigenous communities related to climate and energy. So we have an unwavering commitment to our clients to provide services and support on the journey from awareness to plans through to implementation. We have 49 staff or so located across 28 communities throughout 5 provinces and territories. We bring our collective expertise, experiences, commitment to truth and reconciliation, and passion to reduce local greenhouse gas emissions while maximizing co-benefits so that communities are healthy and resilient. So what does that have to do with high performance building and retrofits? Well, emissions from homes and commercial buildings were 12% of BC's total emissions in 2021. So for us, building better is climate action, and allows us to target a high emission sector while promoting healthier, more affordable, and more comfortable homes in our communities. Through the Kootenay Clean Energy Transition, this is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. We want to help Kootenay and Boundary communities prepare for a more energy efficient and healthy future through training and capacity building, sessions for building professionals, and community workshops that focus on high performance building like this one. So thanks to the generous contributions of the organizations listed at the bottom of this slide, we're able to provide these workshops for free in partnership with building science experts like Murray Frank on the call today. So today's session will be presented in two parts. The first will introduce the basics of home energy, and the second will focus on safety and air quality considerations. If you have any questions as we go through, feel free to raise your hand and I'll call on you to ask your question. You're also welcome to put your questions in the chat. I'll be keeping an eye on them there, and we will be having two separate kind of Q&A sessions after each topic is fully presented. And then at the end of today's session, Lynne with FortisBC will introduce the rebates that are available through FortisBC to help support you on your retrofit journey. And then after the session, we'll just be requesting you folks to complete a really quick feedback poll where you have an opportunity to let us know some additional topics that you'd like to explore in subsequent sessions. And we are recording today's session. We'll be sharing it out with all registrants along with the presentation slides. And that's it from me. It's my pleasure to introduce Murray Frank with Constructive Home Solutions and Building It Right. Murray is a building science specialist and is joining us today to speak to a whole home approach to home energy retrofits and some health and safety considerations. All right, take it away, Murray.
Thank you very much, Janet. That was quite a list of accomplishments there. This observing as people wade through the challenges of energy retrofit in particular is really the only way we learn. Best laid plans and everything. There's nothing like experience to learn and grow from. And we're just beginning to amass really good feedback from projects. I know our own personal home here. We've been on a nice 10-year crusade to do an evolution towards greater energy efficiency of a 1990s home by sort of planning just-in-time replacements as things wear out, windows, mechanical systems, etc. Through planning, we knew, where we wanted to go and where we wanted to eventually go, and it was very helpful in making decisions when that hot water tank goes out and you need to replace it. That's not the time to be thinking about with what. I think what I want to do today is not, I know what we're going to do today is not drill into the nitty-gritty. This is not a how-to. We don't have a chance in an hour and a half to answer all the questions. What I think I really want to focus on to start this whole series is a very high-level sort of helicopter view of what the important steps are if we're going to succeed with energy efficiency. It's a subject that I've been dealing with that's near and dear to me as a lecturer in universities, trade, technical, vocation institutions for the past 40 years now here in British Columbia and internationally, and as a contributor to the codes process and as a very interested personal homeowner as well. I'm passionate about making sure that we do the right things, that we embrace the not only the requirements of building codes, but to deliver on comfortable, efficient, and comfortable homes when we build. So to do this, when we were outlining it, I wanted to first talk about home energy basics, or a more scientific term for this is the basics in building science. What makes a home work? And then in the second part, we want to look at, as we dive into evolving an existing home into a more energy efficient home, what are the tools that we have to help us do that? And what are the potential advantages and some of the challenges that we want to avoid as we move forward? So yeah, I do encourage questions for sure. If it's going to take more to deal with it as we're going along, then I'll defer it and we'll do it at one of the question and answer periods at the end of one of the two sessions. So discover how your house functions as a system and explore whole home approach to upgrades and enhance energy efficiency and comfort. Kind of really important to start with a limit state conversation. What is a motherhood statement? There's only two outcomes, durable, comfortable, affordable house, or something less than that. And it took me a long time to realize that anything short of a durable, comfortable, and affordable home is not the most desirable outcome. And you'll also notice that there isn't big scientific names or anything in there. A durable, comfortable, affordable house is something that that is, I guess, anybody's goal. It's your desire. I'm passionate about this industry, but not everybody's passionate about the construction industry. They're passionate about living in a durable and comfortable and an affordable home. And that's where life happens. So I always want to make sure we come back to that. I will get into some stuff that seems maybe a bit divergent from that, but I'll bring it back, I promise. So what do we need to do? Well, the first thing we have to do is gain a deep understanding of the building science of the home, meaning we need to understand how it was designed, how it was built, how it's performed. And that's important because the same home in 5 locations will perform in 5 different ways. And the unique combination of how a person's home is designed and built and exactly where it's located and even what orientation it takes to the sun and to surrounding mountains and other buildings will have a significant impact on its performance, comfort, cost in maintaining thermal comfort, all of the things that we're trying to improve upon. And in the beginning, we just put a giant heat source into a house and really didn't pay a lot of attention to insulating it or anything. And if you wanted comfort, you just put more fuel at it. And because you were putting so much fuel at it, there was so much energy leaking out through those barriers that you're trying to hold that living space confined within, that heat transfer was taking away much of the risk, which almost always seems to come back to water. Water is condensation, water is a vapor, water is a liquid, water is a solid, snow and ice. And because we had this, the way I lecture it, because we had this virtual hairdryer blowing through our walls and our roofs and even our basement walls, moisture didn't really have a good chance to get a hold of buildings in the past. So I've been asked many times, how come 200-year-old buildings are still there and 20-year-old buildings are virtually disintegrating? And part of the reason is because in the quest for energy efficiency, we've learned that the margin for error is very, very small. Now, can we do it? Absolutely. Can we do it in a cost-effective way? Absolutely. And we've proven it out. But it does mean that we have to gain a deep understanding of exactly how your building was designed and built. And then we need to, from that, select the options that will give you value, quality results that will not create what we call unintended consequences. The building's interesting. It's akin to acupuncture. You know, you have an eye twitch and an acupuncturist will put a pin in your foot and your eye stops twitching. It's not a common sense response, but it's the complex neurological system of the body, and it works. It is something you can't deny it. So in building science, we have to be very careful because the obvious thing, if you want a building to be warmer, is just put more insulation around it. And what ends up happening is, yeah, it might be warm, but you may be making some of that sensitive structure material quite cold because it's further out from the heat source. And now all of a sudden things that used to work stop working. So we want to make sure that we're narrowing the options down to value choices that will not create these unintended consequences. And that's really the challenge of energy efficiency and construction moving forward. And it means you're going to have to engage the services of professionals to help you with tools that can entertain answering those questions for you. And we have them. We have energy advisors. We have processes for determining the power requirements of your mechanical systems. They're actually ingrained now in our building codes, and you have to employ those services in order to build new houses. And it makes sense when you're retrofitting that you would employ those services to help you make those choices. And then create a plan before you start work. I get extremely nervous when people put on the tool belt and start ripping stuff apart without a plan. You may not have things available that you want. You may find that window lead time on one of our projects, we were promised in 2 weeks, and we waited 22 months. This COVID thing happened. And we had a project out of the ground with no windows in it. And what do you do for 22 months with no windows? So a complete plan before starting work, understanding what it's going to take in your supply chain to get everything there. These are all really important things to pay attention to. So understand the energy efficiency improvements. We must understand how that house works. And for that, we rely on the fundamentals of building science. So a high energy efficient home uses several tools from building science, which is a broad science that looks at all of the complex interactions of structural, architectural, electrical, mechanical, civil, all of the components that make up these homes that we love to build and live in. One of the key issues for insulating or for energy efficiency, obviously, and the obvious one is insulation. Something to realize is that there's been magnificent improvements in the selection of different insulating materials that are available to us. We're just in a demonstration project right now with a new product, which is a modified version of an old what they call popcorn polystyrene, that white styrene that you see packaging your goods that you buy from stores. It's a great insulating material, but with the addition of graphite, it becomes almost 20% more effective as an insulator and more resistant to fire. Yeah, I mean, it just means that you're using less thickness of insulation to develop the same kind of blankets. There's spray foams, and we have low density bats, which is sort of the staple that most people know, and the loose filled products. There's blown cellulose and blown mineral fiber was one of the original products that was insulation for homes beginning at the end of the 1900s and into the 21st century. So semi-rigid or rigid boards. There's all kinds of different ones, pink ones and blue ones and popcorny looking ones and smooth faced ones and ones with foil on them. They're all basically the same insulating material, with people looking for marginal changes to make them the preferred choices. Spray applied foams in both rigid formats and in low density or open cell, which are quite spongy formats. Excellent insulating materials as long as they're used properly. We've used them on many new construction and retrofit projects out there. Vacuum insulated panels, aerogels, you may hear things about that. Like a vacuum insulated panel has R values that are just unbelievable, but they're very difficult to work with. And the problem with a vacuum insulation panel is, like it says, it's a vacuum panel. So it's a tremendous insulating product until you pop it, and then it has no R value at all, and it's deep in the structure of your wall. But there is much research going on and much commitment to find ways to use these in effective ways. At the end of the day, at the highest level, it is there to reduce the conductivity through your walls, your roof, and your basements. And we measure that with an R value, which is a resistance value. So the bigger the resistance value, the more resistive it is to energy transfer. And in this case, the energy is heat. We're also concerned about its air permeability because it can double for other functions. In some instances, you want it to be very permeable. In some instances, you don't want it to be very permeable at all. Beyond this presentation, but these are qualities that are all important. Vapor permeability, even more complicated. Vapor is the movement of moisture in its vapor form. You can't see it. By the time it's a cloud, it's actually in liquid droplet form. But there is moisture in the air all around us. We measure that by humidity. And you feel it when you put a rain jacket on and you start working hard outside. That sweat that you create inside and that stuffy kind of damp feeling that you have in all your clothes saturating is because you're entrapping vapor from your body and not allowing it to get through whatever it is you're wearing as a rain jacket. So materials like Gore-Tex, et cetera, are designed to keep the liquid water from going in, but allow water in its vapor format to diffuse through or vent through or breathe through, or many terms that you'll hear. It's a complex notion and it can get you in trouble, but it can also be your friend, and we need to understand it. Density of insulation, application methods, price, availability, all factors that have to be considered. It's a large subject on its own, and I don't want to understate it. I also don't want to have this not moving forward. Never fails, eh, Jenna? There we go. So what's the building science elephant in the room? Water. Water is it's a common. We can't live without it. As humans, we like to live in an environment that has a vapor between 30 and 60% relative humidity. That's just human comfort. So too dry is bad, too wet is bad. A super wet, saturated value, organic material tends to grab moisture out of the air and absorb it into itself, and it bloats and becomes very digestible by molds and mildews, etc. So water in its liquid state, water in its vapor state, water in its solid state are all going to have an effect ultimately on the performance of buildings that we create out there. So first part that I want to talk about is water in its solid format. You can see in this picture, water has an interesting condition when it meets that 0°C or 32 Fahrenheit. It changes from its liquid state into a solid state. And in our houses, this is an example of a okay 1980s sort of code conforming level of insulation in a cold environment, Whistler, where we see snow as well. And that blanket of snow covers the roof areas. Heat loss up into those attics results in that snow melting. It pours off and pours onto that canopy roof. And then it refreezes as it pours off the edge because there's no heat loss from the building directly underneath there. So you get these giant icicles. We get other conditions like ice damming. This can really cause a lot of roofing damage. And in the worst instances, it can back water up and create flooding inside buildings. It can also be awfully dangerous if water in this state comes off at exits and lands on a person. So certainly another thing that we want to make sure we're taking into consideration. And it's going to make me stumble and stumble. The second state of water is in its liquid form. It can affect us through a thing called hydrostatic pressure. That's just a big long word for water that's below the surface of the earth that can affect you in your basements or crawl spaces where you dig your foundations in. It basically, by hydrostatic, means it's water, and by pressure means it's under force. So water under force below the soil level or the grade level of your home, acting on the outside of your foundations, can drive moisture into your basements and crawl spaces. Runoff, and that could be surface runoff around a building, could be runoff from your house through the redirection of water from roofs into valleys, etc. Rainwater penetration. This is a really complex conversation. Rainwater can get through your defense systems of your building enclosure through many different forces acting on it. One is capillarity or wicking of water. So any wicking materials like your concrete foundations will take water out of the dirt and it will absorb it, and it will climb through that material, and it will appear on the inside surface of your concrete, where it will wet up anything that it touches. And it can actually then also re-evaporate in enclosed spaces and create a nice environment for molds and mildews. Kinetic just means that water doesn't usually fall straight from the sky. When it comes in at an angle and you got a hole in the side of your building or through your building enclosure, it can drive through. Gravity is what tends to bring water down to our buildings, and that's why we put so much effort into roofs to deflect that. The toughest one to originally understand is air pressure differential. And the only way that I can really explain this in a simple term is if you were to take a piece of wood, any solid object, and drill a tiny hole like the size of a screw through it and pull the screw back out. If you were to pour water on the backside of that piece of wood, and you were to watch it from my side over here through that hole, you would just see it pouring down across the face of that hole. However, if you were to put your lips up to it and start sucking, you could get a drink of water, because that air pressure differential puts the water in a high pressure zone out here, and it's drawn to the low pressure zone that I've created with that vacuum. So anytime your house goes negative, every single hole that has water in front of it becomes an active leak. And it's not insignificant. It's phenomenal when we've monitored just how significant that effect actually is. In some instances where we've built it in the labs, we put cameras in there, and you'd swear there's aerosol spray cans squirting water in at intervals that equate to the gusts of wind hammering on the outside. But it's the combination of those that make rainwater penetration really a tricky part of the equation. And it was the most significant contributor to the leaky condo. We tried to just create a one line of defense to water with the outside skin of our buildings, and it turns out that rainwater penetration, particularly the air pressure differential, was just contributing so much moisture load into the buildings. That was the same time that we decided to go from 2x4s to 2x6s and go to 5.5 inches of insulation from 3.5 inches of insulation. So the wall was colder on the outside than it had ever been, and it was wetter than it had ever been. And we know what the result of that was. Well, 17 billion and counting in British Columbia. That's what was the math? $3,700 for every man, woman, and child in British Columbia has gone in the repair of leaky condominiums. If you're to average it out, it's a frightening number, and we're not done yet. It's still not cleansed out. So those are unintended consequences, and they were rooted in energy efficiency. We went from a 2x4 to a 2x6 specifically to put more insulation in the wall, and we paid more attention to making it airtight, all with the best intentions, but that was the result. Swelling soils. Soils do crazy things when they're wet and not wet. Some of them tend to swell, and they can create all kinds of structural issues. And then there's construction moisture, the pre-existing moisture in your building materials. At the time of construction, it can create all kinds of things for you. So I'll just let this catch up to our third. We've done solid, we've done liquid. We want to talk briefly about the vapor. We've sort of covered that subject off.
Murray and I were just talking about the joys of PowerPoint before
it's
joined
just
us.
a joy. If I gotta manually push them that way, I'm gonna do it. So rain penetrates if you have a combination of three things. In order to have a leak, you need to have water, you have to have an opening, and you have to have a force or combination of forces acting on the water at the hole. It's impossible to build a home that's never going to get wet. So trying to get rid of all the water all the time is not really a substantial solution. Even if you were able to build the perfect building envelope with no holes in it, who's to say it would be maintained that way? Who goes out on a regular basis and looks for holes in their building envelope? The one thing that we can control, however, are the force or combination of forces. And that's where the capillary break came from. That whole rain screen wall that you hear about, the strapping that now goes on the wall and the cladding being pulled off of there, it just separated the hole in the water from the air pressure differential, which was a gap further in. And so now it wasn't acting at that hole. We took away that force, and it was enough to relieve us from the leaky condo problem when we went to that level of insulation, about an R20 bat on our 15.6 effective. Elimination of any one of these factors will stop the water, but it's important to realize that it's eliminating that one force here. Let's do it the old-fashioned way, guys. I don't have patience for technology issues. Water penetration, driving forces, capillarity, gravity, kinetic energy, hydrostatic pressure, air pressure differentials. Again, we're getting into a too sciencey kind of conversation by the time we get into that part. It's just important to realize that it is sciencey, and we do have the ability to deal with those questions, but that's why it's very important to use the right amount of professional assistance when you're designing and strategizing what it is you want to do. Then you got your vapor contributions of water. You can drive vapor across a building envelope in two ways. You can either have a hole and create an air pressure differential, and then a whole bunch of moisture molecules will just flow through that hole. Or you can have diffusion. It's a much slower, much less significant volume of moisture that will roll through, but it will breathe through like a Gore-Tex jacket. Most construction materials tend to be quite vapor permeable. So what we want to do is we want to have a vapor barrier, and we want to make sure that it's always warm. Otherwise, it becomes a condensing surface. So having vapor diffusion control is important. Having it in the right place is imperative. And controlling for air leakage is extremely important if we're going to get control of the potential for unintended consequences of building science through vapor, through rainwater penetration, its liquid form, and even snow and snow driving up into attic spaces, etc. There's a bunch of other things that can happen with vapor sort of beyond this conversation as well. But you may have heard of truss uplift, and vapor drive lifting flooring is something that I can never leave out of a presentation. And I will promise you a picture of that in a couple of slides here. Primary moisture sources: outdoor moisture, construction moisture, and occupant loads. And people ask me, how much moisture is actually from people, and I'll help qualify that, but it's more than you might think. What affects outdoor moisture? Well, wind can drive it, affects how much rain gets thrown against the building during wet weather. The highest positive pressures at the top and the edges of a windward face. It's also the negative or the drop in pressure that we get on the leeward side as wind vortexes over the top of a house or around the side of it, and that can create a negative pressure, and that can draw moisture, warm moisture laden air outward through your building envelope, and that can be problematic too. So you can get rainwater penetration on one side and vapor condensation problems on the other side of a house. And all of this is if you don't get vapor diffusion control exactly where it needs to be and how it needs to be, and most importantly, if you don't achieve air tightness.
Murray, if it's easier, I could share the slides. You can just let me know when to.
Yeah, if you got them there and you want to go through on the PDF deck that I had there. Yeah, bring them up, then we can switch it over. I'll just mention that sun actually plays quite a role. It helps in the drying of a building. It definitely affects thermal performance. It's also free heat in the winter if you collect it properly, but it doesn't really help you on your northern exposure. So orientation of a house and where you got most of your glass and other factors has to be considered. Just let me know when you want to switch it over here too. There we go. So you might also want to consider too that if you're designing because you've got shade from a forest beside you, and then they knock the forest down and put similar size houses in beside you in 5 years, the whole environmental load on your building is going to change: wind, sun exposure, etc. So understanding what potential changes you may see, and if you can't control them or you're not sure, hedging your bets is a good idea in design. Flip that. Outdoor moisture considerations: groundwater, surface runoff, and poor drainage can lead to water entry and high indoor humidity. I have a great slide that we use in BCIT in the education program there. It's a wonderful tight version of a bottle of Chanel fragrance, and it's got a blurred background, and the bottle's in crisp focus, and it says Chanel basement. And I did that slide to underscore that nobody has ever, nor would I expect would anybody ever invest in a bottle of perfume called Basement. So it tells us what we know about basements. Is that a sign of performance and comfort in a home? Or is that a sign that part of your home is really not a very livable condition and we're just tolerating it? We don't need to have that, but we need to understand how we can build a home so that we don't have to suffer those challenges. A well-drained site will divert runoff and be your friend. Claying soils can have swelling tendencies, as I mentioned before, and that can heave your building around, have great consequence. Talk to people north of Vernon and Armstrong. There's dancing buildings up there that are just exciting. Year over year, they can go up and down 2.5 inches from one end to the other. And we solved it by saturating the ground 12 months out of the year. It just kept it wet and it stabilized. Go ahead. Other moisture, it can come from any direction. So if you want to flip, that's a vinyl, no, actually that's a engineered floor in its planks. And you can see how it's all burped up at the wall there. That is on a basement floor on concrete, and that is a moist concrete slab and that moisture is driving through, turning to a vapor, and the vapor pressure actually lifts that floor. The owner of that floor, every time they go away for a weekend, had to come down and stomp their floor down, burp their floor, they called it. So you see it in obvious forms, and then sometimes you see it in the darndest ways in failure out there. But certainly not acceptable. Go ahead. So the air barrier, 5 requirements of an effective air barrier system. And I wanted to focus on this. You can have the next session is going to be on air tightness and achieving it. It's extremely important for so many reasons. 5 requirements, however, of having an effective air barrier system is that any material you use has to be air impermeable. It has to be continuous. It has to be structurally adequate. It has to be sufficiently rigid or supported to perform as a rigid membrane. And it must be durable. It has to last the life of a building. And you can't maintain an air barrier typically because it's usually elements within the structure of your walls and your basements and your roofs. So there's a lot of stuff that goes on. It's not, you don't buy a bottle of air barrier, you don't buy a roll of air barrier. You buy a series of materials and devices and equipment that in combination, one to the next, are joined in an air impermeable, continuous, structurally adequate, sufficiently rigid and durable method. So that the entire combination of all of those elements works together as one plane of air tightness in the home. If you give a balloon to a child and it's got a small hole in it, are they going to be excited? It's sort of a binary thing. You either have a balloon or you got rubber with a hole in it. With an air barrier, it's not quite as tense as that, but in the 1980s, 90s, even into the 2000s, if you added all the holes in the building envelope of an average home built in British Columbia, it was about the diameter of a manhole cover if you added all the holes up. What we're looking for with high energy efficiency approaching a net zero is a hole the size of a softball or tighter, cumulative in all the holes. And I would also ask that if you made a 100% airtight home, but you cut a big 3-foot diameter circle right beside the front entry door, put the for sale sign in the lawn and had a bunch of people walk through. And when they asked you, what are you planning to do with the hole? You said, nothing. We're all building them like that. Would anybody buy it? I think they would recognize the load on the heating bill, the cooling now that it's mandatory on all new builds. The fact that you're not going to be able to separate that environment from pollens and contaminants outside, that people are going to hear all your arguments because it's a big flanking path. It's obvious what the impact of that size of a hole is when you can see it, but it's not as obvious when it's a bunch of little holes hidden in little places. So we are striving for really incredible performance out of our air barriers because heck, heat energy is just energy and it moves in 3 ways. We'll get to that in the second half here, but one of the ways it moves is convectively. So warm air or cold air that you've spent a bunch of money engineering to be that way inside your house, if it just leaks out, then all the new air coming in has to be heated or cooled again. So the more we can restrict that uncontrolled exit and entry of air, the less money we're going to have to spend on heating and cooling. And that's why it's such a great contributor to energy efficiency. We'll go to the next slide here. There's lots of different materials being used here, a lot of different insulating materials, sheathing membranes, a lot of components. The newer specifications and requirements under the fenestration standards are demanding increasingly higher, and the codes are demanding increasingly higher performance for air tightness, along with thermal characteristics. Different accessories and materials are all being tested at vastly improved. We're even seeing changes in the way houses are being constructed. We're not adding all the beautiful architectural and overhangs and portico roofing and all that nice stuff that makes a house beautiful. We're sort of keeping them in their simplest geometric shape you see down at the bottom there. And then it's really easy for us to get one continuous airtight wrap around that entire house. And those are some of the new hybrid materials. That's a peel and stick vapor permeable membrane that can be applied from the top to the bottom. The lapping is beautiful. The codes embrace it. And it's a very, very effective way of getting the kinds of levels of air tightness we need for advanced energy efficiency. Not the only way. We do a ton with the building wraps, the synthetic sheathing membranes as well, and we've had great success with that, particularly exteriorly insulated. Next one, Jenna. So different wall air barrier systems. You can see spray foam. That's some of the soft foam up there, open cell. You can see there's the sheathing, synthetic sheathing membranes on the outside. No, they were not the cause of leaky condo. In fact, they were quite the opposite for that. Down below, you see drywall with all of the joinery made complete and airtight in there. Although it looks like a regular drywall job, this is being installed as continuous airtight drywall, losing a lot of favor. The old school way, poly with a bunch of tape or butyl sealant, and try and get your air tightness along with your vapor barrier with one material against the bad insulation. This is a pretty old school technique that's losing favor for a bunch of different reasons. We'll move to the next. So rain penetration, driving forces, capillarity, gravity, kinetic energy, hydrostatic pressure, and air pressure differentials. We've talked briefly about all of those. So I want to move to the next slide and kind of talk about how do you design away from that. Well, first thing you want to do is deflect it. Overhangs at the edge of your roof. Good roofing profiles so that the water is channeled to valleys. The valleys are channeled to appropriate drains. The drains are channeled to appropriate discharge. Adding drying potential into your construction. So when it's not wet out, the house can dry and dry readily. So everything that you choose, you need to understand how breathable it needs to be. And then durability, where you know something's going to go into service in a tough environment. Make sure we're choosing materials that have durability for those tough environments. We'll flick just a couple more and then I think we'll get into our break. So yeah, deflection, drainage, drying, and durable materials. If we flick one more here. Construction moisture, there was a lot of concern about pre-existing construction moisture. It's still a concern, you know, and obviously in the wet coast, maybe not in the east and central Kootenays as much, but it's not uncommon to see 6 months of rainfall on a home before it ever gets dried in. And that can put an awful lot of pressure. The materials, you know, are supposed to be 19% moisture content or less before you close them in terms of your main structure. And a lot of times when we go in and take a look at the plates and things that have been soaking in it for 6 months, they're in the 24, 25, 28% range. And there's just a lot of things that can happen when we leave that kind of latent moisture in there. So improving the speed in construction brings economic value and lowers the environmental loads that are imparted on a building during construction. Flick another one here. So reduce construction moisture by ensuring that you're at 19, keeping it protected when you're storing it and testing your lumber before you close it in. It's all tools that are readily available and well understood, but they have to be practiced. Those constant sticking with moisture meters and understanding what the readings mean. I think we'll get a couple more slides in here and then we're just at that sort of 9:40. I do want to just talk about occupancy, moisture, the humidity. How much should people add to the environment? If you flick forward here, human activity comes from washing, bathing, breathing, cooking, and laundry. And if you flick to the next one, you'll see that in new construction, moisture in concrete and lumber can add as much as 4 to 5 liters a day during the first heating season. So there's a substantial drying period in that first year. And then an additional 2 to 3 liters a day come from a combination of clothes and floor washing and use of gas appliance and cooking meals and dishwashing and house plants and showers and baths. 2 to 3 liters a day. And it's 5 to 7 pounds of water. 4 occupants generate 5 liters of moisture per day. 5 liters of moisture a day in the form of a vapor. So if you didn't change that air inside your house and it couldn't breathe out through the building envelope, and we put a vapor barrier in there so it can't, and it can't exchange because you got a really good air barrier in there, then what would happen to your home if you just let people live in them? And the truth is you would blow past that 60% relative humidity quite quickly. So the idea of building a building envelope super tight is not because you want to entrap everything in there. You still need to vent it. And we've built buildings tight enough since the 80s that we can't just rely on accidental ventilation through the holes in the building envelope. So what we need to do is we need to have mechanical devices that can allow us to exchange the air with that good lower ultimate absolute moisture content air from outside and bring it in, and heat recovery devices and energy recovery devices pass it through a heat exchanger. So you get the fresh air coming in, but without mixing, it goes past in the heat exchanger a bunch of chambers where the exhaust air passes. And so all of the heat in the winter that goes out preheats the air coming in. And there's units like the Zender unit out there that will recover 92% of that heat on that fresh air coming back in. So now you're only reheating 8% of it. In the old days, when it was all just naturally accidentally venting through the walls, you had to heat 100% of that air coming in. So the air barrier becomes extremely important for your energy efficiency because it allows us to use tools like that to get a real handle on what your energy costs are. I think that's a good place to sort of leave off. We'll go to the next slide after a question period here, but I think we wanted to open it up. I didn't hear any questions as we were moving along. If there are some questions or some discussion that anybody would like to have, I'd love to hear it.
Yeah, great. So folks, I don't see any questions in the chat. If you would like, you can raise your hand and unmute yourself if you have a question, or you can put it directly in the chat. And maybe while we're waiting, just because I don't see anything coming through, Murray, I have a question.
Sure.
We talked a lot about moisture in the house. So what are some solutions in a retrofit scenario that folks can use? I know there's probably many different solutions.
Sure. Well, I mean, there's so many ways that moisture gets in. So if you're going to retrofit, you have to prioritize rainwater control and ice damming on your roofs. These all form part of your retrofit strategies that may not necessarily have great energy repayment for you, but they're going to save your capital investment in your home. And when you're doing an energy retrofit, if you need to improve, as an example, your roof performance, and your shingles are worn out, and there are some complex details in there, and ice damming is something that's affecting you. And I know in Nelson there's some beauty examples of messed up roof edges that have got all kinds of wire rotters on there and different defenses for it, and obviously Castle in the Cranbrook area, and I've lived quarter of my life buzzing through my favorite part of the world there. And I understand that the kind of damage that you're going to experience just through the environmental loads that you have that aren't necessarily energy related may affect the priorities that you put on your retrofit. You may, I got a choice. I could invest in a new furnace now, but I might have 5 years left in it, or I could invest in that new roof and perhaps even turn it into a conditioned attic while I do it. So I can improve my insulation in the roof. I can get it now up to the roof deck instead of on the ceiling. I can turn that attic into conditioned space, so I can eventually move my mechanical devices up into the attic and get them out of the main floor or out of the basement, and claw back some more usable floor square footage, and get my R values up so the ice damming isn't an issue. And obviously you're going to gain greater control of the air leakage that would be associated with so many ceilings out there. So it's one of the considerations that goes into that complex equation of how do I prioritize, going back to that first slide that I had. It's really being open and honest with yourself and the team that you work with, and talking about everything that bothers you about your home and away you go. I think I saw a question come in there.
Yeah.
Am I right?
Yeah, Sharon asks, she says, I have a rock form basement, styrofoam walls with cement in between. Is this energy efficient?
So with styrofoam in between.
Styrofoam walls with cement in between.
With cement. So it's an ICF, insulated concrete forms. And the question was,
is this energy efficient?
Tremendously. Yeah. Yeah, ICF is it is a phenomenal product. When like anything else, as long as it's assembled, constructed properly, it takes a target load. You want super plasticizers, so there's good flow rate in the concrete. So you want to be working with a placement team and a contractor who have experience. And most of the ICF form manufacturers are in a consortium, and they've done a tremendous job. We actually wrote a guide for ICF construction as a cumulative between all of Nudura and quad lock and all of them. And so as a generic science, they all sort of rely on the same thing and they all share the same challenges out there. Is it energy efficient? Absolutely. I mean, your basements don't need as much insulation as your walls, and certainly not as much as your roofs, because the dirt below your frost line is never going below freezing. So inside 21, outside 0 versus your walls in the winters, which might be inside 21, outside minus 20. Yeah. And the R value of 2 1/8 or 2.5 inches of insulation twice, and its continuity, there's no thermal bridging in either one of those blankets, means you're effectively at 5+ inches of R4 per inch expanded polystyrene. Even some of them even have a graphite polystyrene version, which is almost 5 per inch. So your R value is basically continuous 4 times 5, almost 20. Your 2x6 wall by comparison has R20 VAT, but it's only R15.6. So technically it outperforms by 25%, always has, the walls that are above it, and it's in the less hostile environment. And properly placed, it also puts a capillary break, and it keeps any materials that might wet up through rising damp through the concrete and its wicking capacity inside from its footing. It's not touching anything because that EPS foam doesn't care if it gets wet. So it acts as a beautiful separator from any studs or finishes that you put on the inside. Big fan of ICF for sure.
Great, there you go, Sharon. We do have 2 more questions that popped in the chat, so we'll look at these quickly. John asks, should I design my house to be fully vapor/moisture non-permeable or make it fully breathable? What material should I use to do this?
Well, you don't have a choice to make it breathable at all. Building code requires that you have vapor diffusion control at a rate of 60 nanograms per pascal per meter squared per second. A measure of how much moisture is allowed to diffuse through it per second, per unit area. 60 is what they call 1 perm in the States. They're smart. They use terms that people can relate to. So 1 perm is the maximum permeance that you can have on vapor diffusion control. The key point is you have to stop vapor movement on the warm side, because your 60% relative humidity inside your house at 21 degrees C, if that's what you're got your thermostat set at. Have you ever walked around and gone, ooh, there's a lot of sweat on my kitchen table, or look at the inside of my walls, they're all sweaty? No. So the problem happens when that moisture starts getting through the structure of your wall and through the thickness of your insulation. The inside's 21, the outside's ambient temperature to the world. So in the winter, somewhere through that insulation, it goes from, on a cold day, -20 to a +20. So somewhere in there is going to be a magic point where this no longer just diffuses as a vapor, but it actually condenses on surfaces. So that wetting inside the wall. So to answer the specific question, you have to build it airtight if you want to get energy efficiency, and you have to build it vapor tight, but you have to get the vapor tight component of that assembly on the warm side. But what we're finding is great success if you build your structure out of 2x4s. You don't need 2x6s for structure unless you're building a crazy 3-story plus home. And then the building code will push you to the bottom floor to 2x6s. But we're building most of the homes that we're doing high energy efficiency back down at 2x4s and leaving them empty, putting the sheathing on the outside of the house. And then we're putting the vapor barrier on next as a waterproof membrane. And now it's perfectly airtight, perfectly vapor tight, one material. And then we put all the insulation on the outside of that. There's a great building scientist out there who asked me 38 years ago at a presentation I did at BC Beck when he was still a student, and is now the great Joe Stevebrook, the PhD guy from Building Science Corp out of Boston, and expat from University of Waterloo in Ontario. And he's a great presenter and a tremendous guy to listen to. But he asked me when I presented the coin perfect wall. And I said, really, the perfect wall is when you take all of your control layers and put them on the outside of your building. And put all your sensitive structure, your plywood and your studs and your drywall and your precious art and everything, put them all on the inside. And then realistically, all of your structure is living in the same environment that you live in. And then to drive that home in my lectures, I simply ask the question, if I was to give you a nice little 12-inch long piece that you can tell I'm in construction, I'll go between metric and standard all day long. But I'll give you a 12-inch long piece of 2x4, and I'm going to bequeath it to you as long as you promise that you will keep it under the bed you sleep in every night for the rest of your life, and that you will pass it on to somebody who will take the same love and care and affection and commit to the same handling of that piece of 2x4 for the rest of their life. And then the question I would have is, how long would it take for that piece of 2x4 to rot? Look at all that beautiful old furniture that's come out of old Victorian castles that were far from perfect living environments, that are 4 and 5 and 6 and 800 years old, and they look great. So keeping our sensitive materials in and putting all of our control areas out is a really, really phenomenal way of thinking. The other way is go mass wall like ICF. It's a completely different technology, and all the materials in there don't care about water. They just don't. And they're so massive that the chances of leak water coming through them is very, very limited. And that really is the best way to answer that question.
Great, thank you. We do have a couple more questions here and a couple minutes left before we want to move on to the next topic. So James asks, in an older home with uninsulated walls, where adding a vapor barrier on the interior is not possible, but removing exterior sheathing is, what would you suggest as a means of insulation?
Have to take the sheathing off on the outside, or is it fine? It's an old house. It's probably beautiful shiplap, right? Could be first growth Douglas fir or Western red cedar. Nothing wrong with it. In that case, you've basically got the fixings for a perfect wall. Take your cladding off, take the old building paper off. It's all asphaltic impregnated fibrous material out there. And then just load a vapor and water and airtight membrane across that whole exterior surface. Do a perfect job of it. Primers, rollers, seams, everything. And then add all your insulation to the outside of that, and then use some of the structural offsets and everything. We have a beautiful resource here in British Columbia called the Building Envelope Guide for Houses. You can get it through the province of British Columbia at the King's Printer. And if you want to see about it, you can either Google it or you can go onto the BC Housing website. I'm particularly fond of the guide. I wrote it and the second edition, but it has a ton of these conversations in it and the building science. And you can get it in a digital copy, and I think it's the right, I think it's the right side of $100, $78 or something like that. Download it immediately. It will definitely take you through a bunch of different options, and it will talk about, and then in the third version, it's really going to take it all the way to net zero. And there's a wealth of very good information, and very much picks up where we're leaving off here. Because it's easy to talk about that, but how do you hang cladding 6 inches out through insulation? Right.
Great. And that was a building envelope guide for houses. Is that what you said?
Yep. If you just Google search BC Housing Building Envelope Guide for Houses, go to the page, hit the link, it'll take you to the King's Printer. It is published by the province of British Columbia as a deemed conform document, meaning by consensus through the Engineers Association, Architects, the province itself, BC Housing, the Concrete Institute, the ICF Institute, the Western Wood Trust Manufacturer, everybody. It's deemed to conform with code and represents best practices. It took 12 years to get everybody on one page. So it was a trying process, but it's, and they're now looking to nationalize it along with BC's lateral load guide for seismic and some of the other guide documents that have emerged from here.
Great. I'll make sure to include that link in the follow-up email too, in case you're
sure, and I can forward it to you so you can just get directly to it.
Great, great.
It'll be the best 80. Yep. Go ahead.
Sorry, the best $80. Is that what you could say?
I don't make any money off it. It was a government contract, so I got about 18 cents for it. But you know, we don't do things for the money. We run a research center with no funding. We do it because I don't like lecturing unless I know it's right.
There we go. And then we're just going to squeeze in this one last question. John asks, thoughts on spray foam? Is there not serious concerns for the effect on timber studs and moisture rot?
If used incorrectly, absolutely. If used correctly, I love me my foam. But Kafka has an awful lot of direction on the use of 2-pound close cell. There's half pound, which half pound density open cell is sort of the other major foam that you're going to see out there. I'm sort of moving away from the half pound foams as we get to true net zero, because again, it puts that thermal gradient through your structure because you're filling stud cavities and roof rafters. But in retrofit, it's a very powerful tool. But if you do it, you got to make sure you're using a foam contractor who is checking densities, is specing in spec and invalidate with their A and B reagents, has proper equipment so their gun tip temperatures are right. There's a host of things that have to happen to make spray foam work well. And there is no shortage of people who run down to the States and buy air sealing foam in cardboard boxes and show up with cheap sunglasses and Baja shorts and call themselves a foam contractor. And that will get you in a lot of trouble. That stuff doesn't even have an R value or testing as an insulation. It's just a gap filler. So done well, and if you understand how to use it, and in that guide, there's sections on the use of spray foams, absolutely. Both
Great.
types. Yeah.
Well, we'll move forward to some health and safety concerns, and I might bring up spray foam again in our Q&A there.
No, absolutely.
Okay. All right, so I'll carry you along. Thanks everyone for the questions. That was great.
Yeah,
and I'll just forward us along to the next slide there.
So human comfort is defined at 30 to 60% relative humidity. I touched on that quickly, but I think it's really important. To be honest with you, it's 27 to 55% by ASHRAE, which is the American Society of Heating and Refrigeration Air Conditioning Engineers. But what we found is, particularly in the wet lower mainland, that it is warm enough and wet enough for a long enough period of time in the shoulder seasons in the fall and spring that if we run continuous ventilation, the air outside is ultimately too wet, that if we bring it in, it won't stay below 55% relative humidity. It'll actually saturate you to above 55%. So the answer to that 2 code cycles ago was the government decided to just round it off. So if you round off 27, it becomes 30, and 55, you can either take it up or down. So they took it up. So what it means is you don't need to bring in a mechanical engineer for every home you build in the temperate rainforest in the wet coast. In the Kootenays, you're not worried about that. The air 12 months of the year has value for lowering the humidity inside. So we vent for control of humidity in the houses. That's where and it is based on the expected occupancy of the home. And it expects that the home will be used in a way that's consistent with the average Canadian uses their home. So if you keep your home at 24 degrees C, Part 9 of the building code doesn't help you. It isn't there for overly warm or overly cold occupancy. Or if you choose to drive your humidity up by turning your fans off. And this is not uncommon. We find people that have lived their entire life in the Caribbean or in the islands of Hawaii, they like 80 Fahrenheit and 80% relative humidity. They've lived their entire life at those numbers. So if they come and replicate that within their home, a Part 9 home, a small structure in Canada, won't be able to hold on to it. So it doesn't mean you can't build a house for that, but if you have somebody who wants to live in those conditions, then you do need to bring a building enclosure and a building science engineer in, and they will calculate exactly what will work for those different environmental loads. That conversation aside, 30 to 60 is by far the safe numbers to use for thermal comfort. And if it's too dry, you're constantly drinking water, your skin is dehydrating, it's bad on hair, it's not very nice at all. And if you're more than 60%, it's just muggy all the time. You sweat, it doesn't evaporate very quickly, it becomes inefficient as a cooler for you, which just exacerbates you feeling hot and exhausted all the time. So 30 to 60 is the ideal range by consensus for normal occupancy in Canadian homes. And it turns out that in order to do that based on occupancy, the tables in 932 of the building code for the nation, which is now harmonized across all of Canada, will give you the rates that will ensure that with normal occupancy. Now, if somebody has 35 pets in their house, if somebody has an extraordinary amount of plants in their home, if somebody's hanging all their laundry to dry inside their house instead of using conventional laundry devices, these can be problematic. Operating, hate to say it with Nelson on board here, but operating a grow up, I was involved in a litigation on a new house where it was built as a Part 9 home, not disclosed, used as a grow up, as a conforming legal grow up. But yeah, unfortunately, I learned that you have to be above 80% to force bud effectively. What do I know? But in order to get that to operate as a grow up, it was an admission that it was operating outside these parameters, and so the homeowner lost the case. So 30-60%, if we vent by 932, it will control that. It also turns out that that is more than enough ventilation to take care of carbon dioxide, normal odors, the emissions of toxins, gases, and other things that naturally occur from degradation, cleaning products, all of the other things that contribute potential hazards in our environment. So if everything else is good and you don't have a big mold infestation and you don't have a radon problem for all you Castlegarians there, and surrounding areas, lots and lots of radon questions, the ventilation of your home will not defend against that, not sufficiently. But for everything else, if you vent properly for vapor, you are venting at an appropriate rate to keep the air safe. And the code used to allow you to run it in intermittent cycles. The code now requires it has to operate 24/7, 365 days a year, full stop. And we used to have dehumidistats that would monitor your condition inside the home, and it would turn on bathroom fans and force ventilation when the house got too humid. People would just turn those knobs until the fan stopped grinding in the bathrooms, so that fell out of favor with the building codes. So yeah, they've made it so that we can build without getting engineers in there, as long as we got residential occupancy that conforms with the norm. The general understanding is you're going to sell houses that conform with normal occupancy. And by achieving that control of humidity, you have enough ventilation to take care of all the other things, with the exception of some of those conversations with radon gas and things like that. So outdoor air may be at 100% relative humidity. However, if it's cool air doesn't grab on very well to moisture in a vapor form. So as you warm that 100% relative humidity cold air up, its ability to hold more moisture goes up. And so its relative humidity, which means its humidity level relative to the temperature, will go down. So the air doesn't change as you warm it, but that same volume of air would go from 100%, and if you get warm enough, could go as low as 30% relative humidity. So when we bring outdoor air in, even on a wet, miserable day outside, as long as it is cold enough outside, when you bring that air in and bring it to inside operating comfort temperature, it actually will be lower than 60%, and it will temper or moderate that interior moisture content. During the heating season, outdoor air is cool. The moisture volume is generally lower than the indoor air. So it works very well for ventilation in the fall, works very well for humidity control. In the winter, it can be a bit in the spring. In the winter, it can be a problem because that air in the cold climate regions in the province can be so dry that by the time you start with dry air outside and you warm it up, it is super dry and can create definitely create some humidity concerns on the inside of the building. Again, when you run the hygrothermal numbers on it, as long as that ventilation rate is where it needs to be based on the occupancy, you will still be able to maintain 30% if you get to net zero levels of air tightness and only rely on that air coming in and out through a heat exchanger, and you maintain every drop of moisture that was in it when it came in, because you're bumping it up with the occupancy. Where it becomes a problem in cold climates is when you're under occupied in a house in the winter. You're not generating enough moisture inside to keep it at that 30 to 60% range. So an under occupied home is really problematic in the winter in the cold areas. The recipe is 2 people for the first bedroom and 1 for each bedroom after that. So a 3-bedroom house is expected to have 4 people. If you're living in that house as 3 or 2 people in the cold environments, you may want to add humidification with a device that will only trigger it to get it above 30 and maintain it above 30, but not drive it above 60. Go to the next slide. So we did almost make it through on the first one. I'll hit the next one here. So for modern home to perform, we need a moisture barrier, which is your cladding or your roofing or however you're protecting the outside of your foundation wall. You need a vapor barrier. You can't not have it. And without it, you would have a tremendous amount of challenge. Interestingly, the question about ICF, that polystyrene foam at 2 inches, at 2.5 inches is a vapor barrier. Anything more than 2 inches of concrete fill, and those ICF are typically 4, 6, and 8 inch fill, is a vapor barrier, and so is the foam on the outside. So where's the vapor barrier? Well, the whole wall is vapor tight. So you really don't care which way the vapor is pushing. It's never going to go through the wall, and it's never going to cause condensation because there's no pockets in there for condensation to form, no condensing surfaces. Whereas when you have lightweight frame construction, it always finds pockets and condensing surfaces. You need a capillary break in high moisture index zones, and there's an awful lot of discussion that's quite advanced, and it would not surprise me at all. I'm almost to the point of saying it's highly, highly likely that by 2030, any house built in Canada will be required to have a capillary break behind the cladding. So no more exemption for the lower moisture index regions across Canada. And that isn't because it's suddenly getting wetter in other locations, although you'd be surprised if you look at the wetting maps in Canada, it's like a big U that comes from the west coast and it goes up under Calgary and goes out and swallows up Saskatoon, misses Regina, and is now almost over to Winnipeg, and then it comes back and, of course, widens out and gathers up the whole west coast. All the way in there by the new wetting data is in high moisture index region. So you're on the cusp, and I did that. You're actually in it if you get north of Cranbrook. So right there in Kimberley and areas up in there, you're kind of in the new wetter zone that would trigger it. It's just that's not the reference data in the building code yet. But I will tell you that when you build at net zero, it vastly improves the performance of the wall, and it makes the detailing quicker and less expensive. Gives you a place to dump incidental moisture, so you don't have to put crazy expensive flashings everywhere. You just dump it in the capillary break, and it comes out at the next dissipation point in that wall. Flashings you need to have. We need to deflect. We use drip edges on cladding. We use flashings to keep the moisture load off of the face of the cladding on the outside. You're going to need a mechanical source for thermal comfort. In the past, we called it a furnace. But as of March of this year, all new homes built in British Columbia, must have air conditioning to maintain a maximum of 26 degrees during a heat dome event. It costs you more to put a conventional furnace in with an air conditioner in one room than it does to make the switch over into heat pump technologies in most areas now. And the cold climate heat pump technologies, and I think that's the 4th session, Jenna, isn't it? The heat pump technology. Yeah. So you're going to get a whole, you're going to get a whole fistful of conversation in there about that. I don't want to take their thunder, but I will tell you, 20 years ago, I got laughed out of Prince George when I said you're all going to be putting heat pumps in. And the real estate board just confirmed 81% of new houses built in Prince George are built with heat pumps with cooling capacity. So it's kind of like when I grew up, nobody had air conditioning in the car. Now, I don't even know if you can buy one without it, right? It's once you have it and you see the comfort and, heat dome is, if you believe in it or not, there's some nasty hot days that having cooling makes a lot of sense. And you're going to need a ventilation system, and you're going to want that ventilation system to have energy recovery or heat recovery capacity. And with a great air barrier, that means that you get control of the air going out and coming in, and you're not throwing away all those expensive heating and cooling dollars. But you can also then add filtration on there. from HEPA, so pollen level of desaturation, carbon for odor improvement. And we're using those cassettes on a build that is replacing our demonstration project up at Cathedral Park that burned in the Cathedral Lake wildfire on August 17th last year. So we're 2 weeks away from having that building completely replaced with the next generation version of net zero off-grid demonstration. And we have a beautiful Zender HRV system in there and a wonderful cold climate Mitsubishi heat pump system in there. And we got that envelope so tight, we're at 0.32 ACH50, which is, to put it in perspective, to get passive house, you need 0.6, and we're twice as tight as that. But what was amazing is we don't have any of the mechanical system in there. And we had a week where it went down to 16 in the evening and went to 39 during the day. And it went from 21 degrees to 22 degrees and back every day for that week inside with no mechanical at all. So yeah, a great building, and it's not magnificent. It's just incredibly airtight and extremely responsible to all of the concepts that I'm talking about here. And the little tiny Zender that's in there and the little tiny heat pump that we got in there, I mean, the total mechanical installation with the equivalent to ducted and everything else is less than 15 grand. I don't think you can put ducting in a house nowadays for a furnace only for 15,000. So there is economy in net zero that's available. And in retrofit, a well-designed strategic system so that you're doing more than just doing it for energy. You're doing it to embrace capital renewals of old windows whose time is done, roofing whose time is done, cladding whose time is done, a beautiful country kitchen because the old one just doesn't function anymore. That can make it a far less financial challenge. And do not ignore photovoltaic and collecting your own energy. It's a powerful, powerful tool. We've got well, another day, but we got lots of cool stuff.
Murray, I just want to give you a time check there. We have just over 10 minutes left in the session, and I know we want to.
Yeah, and I think we can blast these ones real fast. Let's hit it. So energy efficiency, what does it take to improve energy performance? Reduce the energy leaking out or sneaking in. That's all you got to do. The building envelope or the building enclosure is in its simplest form, a sphere that keeps the outside out and the inside in. And you wouldn't need any energy if zero was flowing in or out, because you'd set a temperature in there and it would just stay that way forever. Energy is interesting. First law of thermodynamics, you can't create or destroy energy. You can only change its state or its location. So if you had thermal comfort and you had no way for it to escape out or come in from outside, you'd have a perfect building envelope that would need nothing. But you'd have an opposite problem, because then if you occupied it, your basal temperature of occupancy, your human generated heat, would cook you out. When we were building our replacement, we had a crew of 8 people that stayed in our house, and it was 10 degrees out. And they got up at 2 o'clock in the morning, had to open all the windows because they were overheating in the house from just 10 souls in there after a hard day of work, just generating heat inside a beautiful building envelope. So let's go on to the next one. But that's all energy efficiency is. Energy moves in 3 ways. Tough to figure it out. So the first way it can move is conductively. The best way to do this is, imagine if you were holding on to that copper pipe while you were soldering this joint and you didn't have a glove on. What would happen in a very short period of time? You're not hitting it with a heat source, but it's going to get to you by conducting through a conductive material. That is one way heat energy moves. And if you get the next slide, there's a second way it moves. Here's a heat gun. It's got a coil. Through resistance, it heats up. Then it's got a fan, and it takes air and it blows it across the coil, which transfers the heat into that air. And then that fan blows or convects that hot air to where we want to do work. In this case, they're putting a wrap on a vehicle. That's convection. So what is a forced air furnace? Is it a conductor or a convector? It's a convector. There's a third way heat energy works, and it's a bugger to explain. It's radiant energy movement. What I'm going to do is I'm going to prove to you that it's there. There is Sol, our sun. And there's a PV panel. We know we can, whenever it's shining, we can take that energy that comes in and convert it into electrical energy. We also know that it gets really hot when that sun is beating down on us. But what's between us and the sun there? Is there any conductive material? Any brass pipes, or there's not even air particles out there. There's nothing. So what could it conduct through? It can't. Is there a giant fan behind there and pixies throwing dust in front of the fan that warms up as it blows over the sun and then bombards us over here at Earth? No. There's a little bit of solar dust out there, and in the 8,000 years it would take to drift from the sun to us, it would have lost any energy charge that it had to other solar dust or dissipated it. So I'm not going to prove or try to explain radiant energy transfer other than to say, if it can't conduct or convect, what's left? The science to it is, it's just light energy. It's in the infrared spectrum where we don't see it. And so it moves exactly like light, but it actually is heat. That's why infrared cameras can see thermal emissions. They can see body heat coming off. You know, the criminal sitting behind a bush, trembling, thinking that he's so well hidden from a thermal camera. And no, he sees it because the camera is picking up that infrared light, which is that heat energy. So there's three ways that energy moves. We can, if we want to take care of conduction, we got to improve the insulation, and we got to have better quality windows and doors that have good U values. U value is the inverse of an R value. It's just the R value of windows and doors is not very spectacular, and they don't want to advertise this phenomenal R5 window because they're very expensive when we're putting R20 bat insulation into our walls. So they use the inverse, and they talk about conductance, and they get a U value, and it is a real measure. But it just doesn't confuse people with trying to compare it to bat insulation. You just got to buy better ones with low U values. The lower the better for that conductive energy gain or loss. Next slide. If you want to get rid of convection, you just need air tightness. That's it. Everything's got to be airtight as one complete air barrier system around the entire perimeter of your home. That's it. That's all you got to achieve. It also takes care of flanking paths for acoustic. It gives you control of your ventilation system, so you can put heat recovery into it. You can put filtration into it. There's so many things that air tightness brings that it is just the given. And your next session, is James doing that one, Jenna? Yeah, you're going to get yourself a good old dose of, he's an old student of mine from BCIT, and he's an amazing soul. But he's very passionate, and he will definitely show you that air tightness is not an option. And we'll hit the next one here. And for radiant heat loss and gain, realistically, you're never going to, if you had no fenestration or no glass surfaces, no transparent surfaces on your building, you really wouldn't care too much about radiant heat loss or gain. A little bit of surface effect, you can take care of that with some tinfoil on the outside and you'd be fine. But we get an awful lot of solar heat gain through our windows when the sun is shining on them, but we also get radiant loss from us inside going outward through our windows. That's where these low E or low emissivity coatings come in. So when you hear low E glazing, there are different films. Some are designed to keep the heat in from going out at night, and some are tuned to keep the high temperature heat source of the sun from pushing in. So we're at the end of the poll here. Is there any way I can just get one more minute here?
Yeah, you go ahead. Sorry, I was just running the poll in case anyone has to jump off right at 7:30.
Do you want to just flick to the next one here? So yeah, if you could move that poll over too, because I can't see mitigating.
I think that's on. That might be on your screen there, Murray.
No, is it okay? Oh, so you sent it to me. Oh, it was amazing. Mitigating the risk needs to improve insulation. I did see a comment in there too, an opinion when we were talking about radiant. So I do want to give a minute to read what that was. Need to improve insulation, but this can increase the risk of condensation or accumulation of moisture in the wall. No longer a strong drying force passing through the building envelope. We talked about that. Flick to the next. Need to improve the air tightness, but this on the right there is a manometer. We use door fans. We can test and give relative measures in two different ways. One's volumetric, the air changes per hour, 50 pascals. There's a new one that is much more fair to the area of the building envelope. But no matter how you're going to measure it, you need better air tightness moving forward into energy. It is the low-hanging fruit. You can't create a problem for yourself by going airtight, and you can't go backwards to the time when we didn't need air tightness. Those days have been gone for 40, 50 years almost here in Canada. We've coded ourselves to a higher expectation than that. So, but understand that there's no longer a strong drying force passing through the building envelope by not allowing warm air through there in great volumes. So we got to mitigate that risk. We got to make sure that if you're going airtight, you want to go all the way. Remember the child in his balloon, or her balloon. Next slide. Mitigating the risk, need to improve heat reflectance in your windows, but that can decrease free heat in the winter. So on the right there is a TECA, and that is a F280 report, CSA F280 report. This is one of the tools along with the EnerGuide Hot 2000 reports that you must engage if you're going to retrofit. The EnerGuide gives you a whole metric of how much energy you expect the house with the changes to use over a year. This one tells you what the peak demand loads are going to be for the maximum heating days and the maximum cooling days, so you can right size all your equipment. The combination of those are must-haves. Otherwise, you're going to put in too small or too big or too many heating and cooling devices. And so much money is being spun right now because of that. So do not be afraid of engaging the professionals who provide these services. And in new construction, you can't build without their involvement. And for many of you, and I believe we're going to have Fortis make some comments here, for many of your incentive programs, you're going to need at least your Hot 2000 EnerGuide report. And I believe increasingly people are also going to ensure that you've used an F280 so you've right-sized your equipment. And where can we go quickly here? Mitigating the risk. What do we got next? Next slide.
Yeah, it's not moving forward.
Oh, then I guess we're at the end.
All I've got. Yeah.
I think that's where okay. So I ran a little long. I'm sorry, but I'm passionate and I love it. But thank you very much. I appreciate it. Do we have a couple minutes then for
we do. We have 2 minutes, and the comment in the chat was just a little silly comment to when you were trying to when you're describing the sun. So it's not a direct comment.
I want to see it, but give it to me later.
He says, according to my beliefs, there are pixies behind the sun with big fans.
Yeah. As soon as I saw my beliefs and I couldn't see the rest of it come up, I thought, yeah, I want to hear that one. That's awesome. I do too, that, but James. I don't get anywhere with it, James. All right. Well, any other questions, or can we invite Fortis to take the helm here? Oh, Greg.
All right, Greg. Will an owner recover the cost of a 3-pane window versus using 2 panes?
I'm going to say that we have been shocked with the windows that we've chosen. You can get there with an S4 coating on a double glazed window assembly. But I think triple pane glass is going to be the future in all of Canada. Yeah.
Great, thank you. Oh, perfect. We've got the next presentation up there and ready to go. Okay. Okay, great. Okay. Well, thanks very much, Murray. Thanks for sharing all that information with us. I really do appreciate it. And I know Murray kind of he alluded to a few more webinars that are coming up in the series, so I just popped the link in the chat there if folks want to check it out. And now, so yeah, thanks again, Murray. Thanks so much for your time.
Thank you.
And we're just going to pass things over to Lynne at FortisBC. She's going to take us through some available rebates for you folks. Thanks,
Lynne.
Thank
you. Yeah, thanks, Jenna. Murray, that was an excellent presentation. A lot of information there and really good information. So really appreciate that. My name is Lynne Williams, and I am the program specialist for conservation, education, and outreach at FortisBC. And I'm just going to share some information with you on our residential rebate programs, that's hopefully going to help our customers offset the cost of upgrading old equipment to new energy efficiency equipment and to do improvements. Because as we know, these improvements, they can cost a lot of money for sure. So we definitely want to help people be able to afford to make these improvements and provide some incentives. So I'm just going to go through our dual fuel heating system, our home renovation rebate program, and some of our electric rebates. So I'm not sure if you're aware, but 64% of the energy used in your home is for space heating and 17% is water heating. So this is where you may want to focus the investment in energy efficiency equipment and improvements in your home to save energy, because it's a lot of energy lost can be lost in space heating. So the home renovation rebate program, what is it? Well, it's one of our most popular programs amongst our residential customers, and it includes upgrades in existing homes and offers rebates for space heating, water heating, building envelope, which includes insulation and windows. And then we also have bonus offers. So we encourage our customers to complete more than one rebate. And if you do that, then you will see bonuses for doing this, and it ties into the whole home approach. And then we also work with industry to build capacity and create installation best practices, and that's for contractors and for manufacturers. So basically, general eligibility is you must have a residential account with FortisBC Natural Gas or FortisBC Electric, and electric territory is in the City of Penticton, the City of Grand Forks, Nelson Hydro, and District of Summerland. And if you are in other areas of province, then that is BC Hydro that you would look to for providing your rebates for that. You can also go onto the Clean BC website, and that gives the rebates for BC Hydro and for FortisBC, and also if there's any federal programs, which there used to be the Greener Homes program, and they've actually stopped that program, but I'm hearing it's actually coming back, I think, for medium and low income. So your home must be a year-round residence. So that means it cannot be a cottage or a vacation home, and at least be 12 months old. And you're not eligible if you have your new additions are, new additions are not eligible, and customers must be upgrading an existing space. Upgrades to the garage, workshop, and outbuildings are not eligible, as is existing spaces converted into a living space. And applications must be submitted within six months of the invoice date, and all installs must be completed by a licensed contractor with a GST number and a valid BC business license. So no self-installs or do-it-yourself jobs. Those won't be eligible. So the general eligibility for homes is they must be single-family detached. Secondary suite in a single-family detached must be individually metered, or duplex, triplex, row home, or townhouse, or a mobile home on a permanent foundation. And why we're doing this is to provide rebates. We must be able to claim cost-effective energy savings, and single-family homes allow us to do that. So the provincial Clean BC Roadmap for 2030 that was released in 2021 targets reducing provincial greenhouse gas emissions by 40% below 2007 levels by 2030. So the roadmap encourages the installation of dual fuel heating systems. So our dual fuel heating system rebate helps offset the cost of installing a new electric heat pump with a new high efficiency gas furnace. And when you install a qualifying dual fuel system, you'll have access to both a reliable and efficient heating system to keep your home warm and comfortable, and that's even on the coldest days, while also benefiting from cooling on hot days, and a system that can be more than 100% efficient under certain conditions. So the dual fuel program offers a rebate of $10,000 for installation of a dual fuel system, and this applies to natural gas customers looking to replace older inefficient furnaces, 10 years plus years old. And in addition, an incentive of $300 will be available to installation contractors, and that's to drive quality installation initiatives, and that includes right sizing and commissioning. So Murray pointed out that, yeah, nobody was doing heat pumps a while ago, and now everybody's doing heat pumps, and they can be quite expensive. So this is a pretty good rebate offer. If you're an income qualified customer, then it's a $15,000 rebate. And also Indigenous communities, part of our conservation program is also a $15,000 incentive amount. And then there's a Northern offer top up of $3,000. So pretty good rebate. So we're hoping people will take advantage of that. Then, so we also have the connected thermostat rebates. So these must be installed at the same time as the new heating system is installed or as part of a maintenance program for your heating system. And the new connected thermostat must be listed on the eligible page. I've got a link here that tells you what models are eligible, and maximum 1 connected thermostat rebate per home. And these are just examples of what these thermostats look like. So insulation rebate requirements must be installed by a home performance contractor network member. Self installations are not eligible. And the Home Performance Contractor Network is a database of retrofit contractors in British Columbia that meets specified trade designation and training qualifications, and they're subject to ongoing review and quality insurance checks. So these are the eligible locations for insulation upgrades. So that's the attic, flat and cathedral ceilings, exterior wall cavities and exterior wall sheathing, and other exposed floor or floor over basement crawl space and basement crawl space walls. And then these, Murray kind of went through this already. These are some of the types of insulations that we are eligible for the rebates. So that includes batt insulation, loose fill, spray foam, board, and then aluminum and soundproofing. These are not eligible. Then we have window and door rebates, and the specific requirements are that they must be installed by a licensed contractor. Again, self-installations are not eligible. They must be replacing existing windows and doors. Skylights are not eligible. And the window door installed must have a Natural Resources Canada NRCan or Certified Products Directory number provided by one of the following certified bodies. And the manufacturer labels for each window or door must be submitted alongside the invoices. So window and door rebates. So the U factor can be expressed in imperial units and metric units, and our rebate requirements are expressed in metric units. And the rebate amount is $100 per window or door up to a maximum of $2,000. Then we have our air source heat pump rebates. So these electric rebates are provided by FortisBC in our shared service territory and electric only territory, which is Kelowna, parts of the Kootenays, and the southern interior. And the rebate amounts are ductless mini split heat pumps, $1,200, and for ductless multi-split heat pumps, they're $2,000. And then central ducted heat pumps, tier 1 are $1,200, and the central ducted heat pump tier 2 are, oh, got a missing a zero there, but they're $2,000. And again, in the electric service territory where BC Hydro operates, then they would have rebates for electric heat pumps as well. And you can just check the BC Hydro site, or like I said, the Clean BC site. Then there's heat pump water heater rebates. And then again, these are provided in our shared service territory and electric territory. Again, Kelowna, parts of the Kootenays and southern interior. And they are up $1,000. And it must be a qualifying model. Again, we have the link here that goes to our page, which lists all the qualifying models. Then we have our bonus rebates. So again, said if you do multiple upgrades, then we have a 2 upgrade bonus, which is an extra $300. No evaluation required, and the customer must complete 2 bonus eligible upgrades. And then we have the home energy improvement bonus, which is from $750 to $2,000. This is a little bit more involved. So the customer must have a program qualified energy advisor, perform a pre and post energy guide evaluation, and the customer must complete 3 bonus eligible upgrades. So the customer can receive either the 2 grade or the home energy improvement bonus, but they can't have both. So just one of those. Then we have additional rebates for FortisBC electric customers. So we have the heat pump service, which is $50 rebate, and the application must be submitted within 60 days of the service invoice. And then we have the Energy Star appliance rebate. So for a clothes washer and dryer, that's up to $250, and refrigerators are up to $100. And you must purchase a qualifying Energy Star appliance, and the application must be submitted within 60 days of the appliance purchase delivery date. And, oh, I went too far here, sorry. But you can apply online, and that just rebates at fortisbc.com, and we've got all the information there on all the rebates and how to apply, or you can call us Monday to Friday, 7 a.m. to 8 p.m. Pacific Standard Time, and get a customer service person that can help you with any of this information. So, or you can contact me if you want any additional information, and I'll happy to provide that for you. So yeah, thanks again for letting us let you know about our rebate programs, and if there's any information we can help you with, we're more than happy to do that.
Yeah, wonderful. Thank you. We did have a couple of questions come through the chat. So just to clarify, Richard missed the beginning, but you said the rebates apply to Penticton, Summerland, Grand Forks, and Nelson. Do they apply to New West as well?
On anything for electric, yes, it does apply, but you'd have to go through BC Hydro. We provide electricity to those areas, some of the areas in the Kootenays and the Okanagan, but BC Hydro is the electricity provider for the balance of the province.
Perfect, thank you. And then I know you did touch on some rebates for heat pumps. James just asks, he says, a main goal for my retrofit is to eliminate fossil fuels. Do FortisBC rebates apply to projects switching from fossil gas to electric?
In their electric service territory, they do. In other parts of the province, no, you'd have to go to BC Hydro because we're offering the dual fuel heating system offer, which is a combination of the gas furnace with the electric heat pump. Which is we found especially good if you're in like cooler climates, because you can use the gas furnace in the cool periods, and then you can switch to the electric heat pump in the spring and summer months.
Yeah, great. Well, wonderful. That was a great overview. I know there's a ton of rebates out there, and it can be really difficult for folks to navigate and understand the big picture. So thanks so much for sharing that with us today, Lynn. And thanks again, Murray, for your great presentations, and for everyone on the call for joining us tonight. I will send a copy of the presentation slides and a recording of the webinar and some more information about our upcoming webinars in a couple days. So yeah, thanks again, everybody, and enjoy the rest of your evening.
Thanks, Jenna.
Thank you.
Okay, bye.
Bye-bye.